Good morning, everybody. We are discussing the bilge water separation, water and oil separation. We have started already few things on water separation. For example, emulsion, how emulsion is getting formed and how demulsifier is being added. So here one example is given from one company, RX Chemicals. So they produce bilge water flocculants. So this is actually polychloride they are saying. So this is I'm giving just for an example how this flocculant will be added in a bilge water, so that bilge water emulsion can be broken and will be separated. So this is oil water separator thing, oil and water separator. So separator oil reduces from bilge water uh, if it is iron free and completely safe to environment. From the company document I am reading, so this is exactly copied from a company document. So international environment regulations is this, it will be your oil content should be less than 15 ppm. So typical dosage rate 100 to 500 ppm in a multi-stage bilge water cleaning system. Bilge water flocculant is fed undiluted through a dosage pump. So it's called dosing pump, chemical dosing, the term is used. Okay, so floc tank is fed according to the flow of the bilge water pumped into it. The feed is adjusted in connection with the installation and normally needs no alteration. If required, dosing pump can also be controlled by measuring the level of the container. Okay, so this is exactly from the RX Chemical company website or product brochure. So whenever you're talking about oil and water, so water is here and oil particle there. So oil particle moving up. So actually oil particle will be settling. Okay, so oil particles will be settling. Okay, settling means it will be floating, it will be creating one layer here above water. Now what will be the velocity of the oil particle so that your retention time will be lower? So retention time lower means if accordingly you can design your settling tank. Settling tank sizing, for example, in the input is here and output is here, say in inlet outlet of water. Inlet may be oily water, outlet also will be oily water because 100% oil you cannot remove from here. So again it will be like, I cannot write like pure water, it will be oily water again, but reduced oil content. Okay, reduced oil, I can write reduced oil content in water. Okay, now if I know the settling time very low, then my separator sizing or settling tank sizing will be lower. But in some case, if we have very large settlement time or the oil particle velocity very low, in that case your tank size will be very high, your large tank size will be required. So for that we need to create one formula. You may remember this is your particle, and if particle is moving up, let's say this is oil particle in water. So oil particle is moving up and water may be flowing down or may be fixed. So in that case oil particle will have drag force Fd, drag, and its own weight F weight, and buoyancy force. So buoyancy force is pushing it up, while drag force will be pushing it down, and its own weight it will be downward. So this way the particle will be moving, but it will get three forces. Now rho density, rho p density of oil particle, and rho f density of fluid of water. I can write rho w, that is better, and rho p I can write rho oil O, and mu is viscosity of water. Okay, because if water viscosity very high, then particle will try to move, but it will get more drag force. Okay, Fd related to drag force related to viscosity. Okay, so drag force Fd or drag force F drag force Fd. So from there CD, coefficient of drag or drag coefficient equals Fd half rho water u velocity A means area. It is completely sphere, so it will be surface cross section area. Of particle or oil particle. Okay, what is continuous phase? So water is not having particle now, we are assuming, and oil is the particle. We assume the oil particle having spherical dia, and spherical dia normally the drag coefficient in water will be like 0.5 or something. Okay, now F drag Fd equals mg. M is the weight, mass of oil particle, g acceleration due to gravity. So we have one Stokes law. This is called particle settlement. Stokes law, and condition is that Reynolds number must be very lower than 1. So Stokes law says Fd equals 3 pi d mu Vs or V settling. Settling velocity. Now mg equals rho particle means rho oil into volume is pi dq by 6 into g. Okay, now volume equals pi dq by 6. Now settling velocity Vs is settling velocity is equals rho oil into g d square 18 mu. So here mg equals should be rho dash. Okay, rho dash. So rho dash should be rho water minus rho oil. Okay, so this is your formula. So criteria is that Reynolds number should be less than very less than 1, and d should be more than mean free path. Or in simplified form we can derive like this: Vs equals root over 4g rho w minus rho oil, because rho dash we have written rho w minus rho oil d oil square 3 c d rho. So c d equals 24 by re. This is laminar flow. Okay, so re becoming d oil u oil rho by mu. So u Vs equals g d square rho water minus rho oil by 18 mu. Let's take a simple problem. Reynolds number of 10 micrometer diameter spherical powder particle drug. Okay, specific gravity also given, is settling in room temperature in air. So in that case instead of water they have taken some particle and it is air. So to solve this one, rho particle is given 1.2 126 into density of water. Equals 1260 kg per meter cube. So viscosity of air equals 1.8 into 10 power minus 5 kg ms. Density of air equals air 1.2 kg per meter cube, which gives V settling 1260 into 10 power minus 6 divided by 18 into 1.8 into 10 power minus 5 kg meter second. So this is giving 3.8 into 10 power minus 3 meter per second, so equals 3.8 millimeter per second. So Reynolds number V relative d nu equals 3.8 into 10 to power minus 3 into 10 power minus 6 divided by 1.5 into 1 minus 5. This is giving 0.0025. So this is very less, lower than 1. So this is assumption is correct, because Stokes law says it must be very less than 1. So we see another problem: discrete particle settling in water. Given data, diameter of particle and specific gravity, it will be almost sand. I think sand will be 2.6. So kinematic viscosity is given for water. Water density also given. So terminal velocity Vs, settling velocity, terminal velocity have to calculate. So dynamic viscosity of water is given 2 into 10 power minus 6 into 1000. So 2 into 10 power minus 3 kg meter second, and V equals 2.65. Better will write the formula. Rho minus rho particle minus rho water, g d square 18 mu. So rho particle is given 2.6 into 10 to the power 3 minus 1000 or 10 to the power 3 into d. Particle size is given 2 into 10 to the minus 5, 2 into 10 power minus 5. This should be squared, and g value 9810, 9.81. Okay, and this one 18 into viscosity given 2 into 10 power minus 3. So this value is giving 0.000179 meter per second. So it is giving 0.179 millimeter per second. Okay. So coalescence, when two particles are meeting each other, they will make bigger particle. So they will coalescence. So coalescence formula is like this: T equals pi by 6 d power j. So I'll write again: T equals pi by 6 d power j minus do j phi ks. Okay, and it is simplified form: T equals pi by 6 d power 4 minus do power 4 by phi ks. And if we make further simplification, it will be like d power 4 pi 2 phi ks. Okay, so here do initial droplet size, and after meeting they will be growing. So d is a final droplet size, phi is a volume fraction of the dispersed phase, how much dispersed phase is there. Dispersed phase, this one, oil. Then k is empirical parameter of the particle system, j is the empirical parameter, more than 3, and depending on the probability that droplets will bounce apart from each other. T is time to grow in size. So when energy of oscillation, particle will be oscillating inside the fluid, so energy of oscillation is low, J we can take 4. So in that case the formula will be simplified as T equals pi by 6 d power 4 minus du power 4 by 5 ks. So this will be your formula. Now do, if do is very small, then we can ignore and formula becomes T equals pi by d power 4 to 5 ks after approximating it. So this is called time to grow, droplet in coalescence due to coalescence. Okay, so minimum time required, this is T equals minimum time required to obtain a particle size d.